Okay, this is the heating curve lesson that goes along with the thermochemistry unit. So, you already know Q equals MCAT, and you already know Hess's law. So, this is just kind of where we get some of those calculations from, or how we use the Q equals MCAT to determine the amount of energy required or released in certain physical only processes. Okay. So it says, what happens to the temperature of a block of ice when you put a Bunsen burner underneath it? Well, the temperature goes up, but that's not all, okay, because it will eventually melt, and if you keep the heat on, the temperature will still increase until it gets to a boiling point, and then the water will convert from a liquid into a gas, and that's called vaporization. So those are all physical processes. This is all describing just physical processes, okay? So this graph right here, this is called a heating curve. This is the heating curve for water. And it shows we have some constants. It says the constants for water are as follow. The specific heat of solid is 2.03 joules per gram times degrees Celsius. The specific heat of liquid water, you already know, is 4.184 joules per gram times degrees Celsius. And the specific heat of a gas is 2.01 joules per gram degrees Celsius. The heat of fusion, which is what happens when a solid melts, or if it goes the other way, if it freezes, and that's 6.01 kilojoules per mole. Nobody really uses that number, so we're gonna use joules per gram instead, because that's a little bit easier to use for your calculations. Okay, so that number is 333 joules per gram. And then the heat of vaporization, so that's the heat either required or released when a liquid vaporizes, or when a gas condenses back to a liquid. And instead of using 40.07 kilojoules per mole, because again, that's in moles and most of our measurements are in grams, we prefer to use 2,260 joules per gram. Okay, so those are all the constants. You don't necessarily need to memorize the constants, but given any quiz or assessment, these are the constants that will get you to the correct answer, typically. Okay, all right, so let's talk about this heating curve for water business. So what's going on here? So down here at the bottom, okay, down here where it's very cold, see, this is temperature on the y-axis. So below zero, what state is water in? Hopefully you got solid. So down here it's a solid, okay? So here between 0 and 100, so 0 is water's what? It's water's freezing point. It's not every substance's freezing point, but see where this flat line is? That means that's water's freezing point. That's the point at which water turns from a solid into a less condensed phase of matter. So the next less condensed phase of matter is what? What would water turn into at the freezing point or melting point? It would turn into a liquid. Okay? So at the freezing point, you can add or remove heat to change the phase of water from a solid to a liquid or from a liquid to a solid. Okay? So up here at this next flat line, if you notice, this flat line occurs at a temperature of 100. That would be water's boiling point, okay, is 100. So that's the point at which it vaporizes. So it'll turn from a liquid into a, what would be the next less condensed phase of matter? A gas. Okay, so what's occurring here? Well, as we increase the temperature, okay, so if we're going up this, we're increasing the temperature, we're using a positive Q equals MCAT. So anywhere where there's a slant, I'm going to do it in a different color. Anywhere where there is a slant, the Q equals MC delta T. That's the equation we use for that. Anywhere where there is a flat line, okay, Q is equal to M times an enthalpy, and the enthalpy is for whatever the process is, okay? If the process is melting or freezing, we're going to use the heat of fusion. If the process is boiling or condensing, we're going to use the heat of vaporization. Now, these constants that you see, the C's and the delta H's, those are different for different substances, but we're going to concentrate on just water for our course, okay? You may have to do different substances later on in AP Chem or in college, but for right now, we're only going to worry about water, okay? Okay, so if we're going up, so if we're increasing the temperature, you're going to have a positive Q value because your delta T, it's final minus initial. 0 minus negative 20, 0 minus negative anything is a positive number. So if this is a positive number, then your Q will be a positive number. If you're going this way, so you're adding heat, but look, the temperature stays the same. That's why it's a flat line. So if you're adding heat, but not changing the temperature, you have hit a phase change. And so for flat lines, you have a phase change. You're going to use Q equals M something, right? In this case, since we are melting, it's going to be Q equals M times the heat of fusion. And you're going to use the positive of the heat of fusion to give you a positive Q value. Okay? Once it's all become a liquid, then you can, as you add heat, the temperature will rise. So as the temperature rises, again, you're going to use a Q equals MCAT. And if you have any number greater than 0 between here, your Q equals MCAT will be a positive number, so you'll have a positive Q value. Okay, now up here, you can add more heat, but look, the temperature doesn't change. The temperature never changes during a phase change. That's very important, okay? Never changes during a phase change. You can add heat, but you cannot change the temperature. So liquid water at atmospheric pressure cannot exist above 100 degrees Celsius. At that point, it vaporizes. So since it vaporizes, the Q value, it'll again be positive, okay? And it'll be equal to mass times the heat of vaporization. And you're going to use the positive of the heat of vaporization to give you a positive Q value. And then once it's a gas, if you continue to add heat, okay, then this will also increase the Q value again. And so any number greater than 100 minus 100 will give you a positive delta T. So you will again have a positive Q value. Okay. I don't like that this y-axis down here says time. I think it should say heat. Okay? Because as you're going that way, you know, up, right? Okay? As you're going up, you are adding heat to the system in order to get it to go to these different intervals. Okay? Now, if you take heat away, if heat is released, that means you're cooling, okay? So absorption of heat energy, okay? Energy. Absorption of heat energy is an endothermic process, which means everywhere where you're heating or adding heat, okay, is an endothermic process. Okay, so if we go backwards the other way, so if we have a gas and we start as a gas and we decrease the temperature, then our final minus initial, so 100 minus 120 will give us a negative delta T value. So as we cool the gas, that gives us a negative Q value. So as we go from gas to liquid, okay, we're going to be condensing. And as we condense, we can't make mass negative, but the delta H will have to be negative, because the reverse of the heat of vaporization is the heat of condensation, and that is a negative delta H. So you'd stick a negative in front of that 2260 when you stick it in your calculator, and that'll give you a negative Q value. Okay? Then when it's all become a liquid, then you can cool it down some more. And as you cool it more, your final minus initial temperature, 0 minus 100 gives you a negative T value. So that will give you a negative Q value. So then once it's all down to 0, then we can freeze it. So as you freeze it, as it goes from a liquid to a solid, going this way, you end up with another negative Q value, because your delta T, because your heat of fusion right here, your heat of fusion, the opposite of that would be the heat of freezing, right? So that, which is not really a thing. So you just use the negative of the heat of fusion when you're freezing something. And then for this part, because you're going down, decreasing in temperature, your temperature would be final minus initial. Negative 20 minus 0 is a negative delta T, which would give you a negative Q value. Okay? So if you are cooling, so if you're going right down the thing, you are cooling. All cooling processes, in order for the matter to condense more, okay, it has to release heat energy. So it would be what you call exothermic. Okay, and I know a lot of you are thinking that's wrong. Exo means it gets hotter. No. Exo means that a system is releasing energy, which means the surroundings might get hotter, but the system itself will not. The system itself will not get hotter. So, all right, so let's look at this a little bit more. Let's think about what the matter looks like at these different phases, right? So as a solid, your matter is very, very, very well ordered. Okay, you've got particles that are stacked on top of each other, right? And as they heat up, they're basically not really moving. They're just vibrating about a fixed position in their matrix, okay? But as they heat up, they vibrate faster until they're vibrating so fast that they overcome the intermolecular force of attraction that's holding them together. And then you end up with a liquid, okay? Now a liquid is going to have less order, but the particles will still be relatively close together, right? Okay, so they're still relatively close together, so they still have some intermolecular force of attraction that's kind of keeping them together, okay? So in order to go from a more ordered state to a less ordered state, you have to add heat energy to overcome those intermolecular forces of attraction, okay? So that's what the heat of fusion here represents. It's the heat required to break the intermolecular force. So what's happening here is the particles are vibrating in that slanted portion. So this is increasing the kinetic energy. Temperature is a measure of kinetic energy. So you're increasing kinetic energy right here as you're raising the temperature of ice. But when you get here, you're not raising temperature anymore. So you're not changing the kinetic energy. So here what you're changing is the chemical potential energy. And that's the energy that's stored in that intermolecular force of attraction, keeping these particles together. So once you give it enough energy, you break those forces of attraction. You've utilized heat energy to break through all of the chemical potential energy and make those particles spread apart. Okay, so as a gas, the particles are really far apart, right? They're really spaced far apart. And they have almost no intermolecular forces touching them, draining any of their energy, nothing like that, okay? So if you look here, this line is representing where we had to input more energy in order to go from a liquid where we have a less condensed state of matter than a solid, but not as free as gases. So we input more heat energy to break the intermolecular force of attraction, keeping these as a liquid, okay? And so, then for this slanty line, remember you're increasing kinetic energy. But for this flat line, you're increasing chemical potential energy that goes into decreasing the intermolecular force of attraction, allowing the particles to spread further and further apart. So this is an even less condensed state than a liquid because of that. Okay, so you do need to know, where do you see, where is there a kinetic energy situation and where is there a potential energy situation, okay? And so for every slanty line, okay, for every slant line, okay, this is telling you that there is a change in kinetic energy. For every flat line, this is telling you that there is a change in chemical potential energy. Okay, so that's important to note. Now, you're adding energy to go like up the curve, and you're taking away or releasing energy to go down the curve. Okay, so you have to remember, where are the potential energy? In the flat places. Where's the kinetic energy? In the slanty places. Because kinetic energy is a measure of temperature, and chemical potential energy is used to break or form intermolecular forces of attraction. Okay, so that's pretty much all of the conceptual stuff, all in this one little thing. Okay, one more thing I wanted to note is, you see how this line is longer than this line? It requires more energy to break intermolecular forces from a liquid to a gas than it does to break the intermolecular forces holding a solid into a liquid. So this line will always be larger than this line for any substance, but specifically for water, it'll be bigger. And that makes sense because look at the two different heats, right? The heat of fusion is 333 joules per gram. That's that little line. Okay, the heat of vaporization is 2,260 joules per gram. That's a lot more energy, and so that's a much larger line. Okay, it's typically not drawn perfectly to scale, but you should see this line bigger than this one because this energy is greater than this one for the same exact mass. Okay, all right, so that's all the conceptual. So let's talk about the math. So again, we're going to use these, what do you call them, constants, and there is one thing kind of worked out for you, and it's done in this weird little stepwise fashion. And again, I don't like that we don't have a 4 in our 4.184 joules per gram times degree Celsius. And then we don't really like to use the 6.01 kilojoules per mole. We prefer to use 333 joules per gram. And we don't really use the 40.7. We prefer to use 2,260 joules per gram. Okay, so those are better and easier to deal with, okay? All right, so let's talk about calculations. So I'm not going to go through the example that's already there. And it's nice that it goes through each individual step, but it also uses that kilojoule per mole situation, and that is not my favorite. So I'm going to bypass that example and go straight to example 2. All right, so here we go. So example 2. All right, so it says, how much heat would it require to raise the temperature of 4.50 grams of water from -3 to 55? All right, so what I like to do is, off in the left-hand margin, I like to draw the little heating curve for water. And these are all going to be for water, thankfully. If it says steam, it's talking about water. If it talks about ice, it's still talking about water. So all of these constants will still apply because these are all for water. Okay? All right. So I like to draw just on the left-hand margin, I like to draw my little me. Okay? And so I know that I'm going to start at -3. So I kind of start down here and I say, okay, well, that's -3. And then I need to go to 55. So 55 is going to be like right there. Okay. So that means I'm going to go from -3 to 0 because I have to go through 0. Okay, and then I'm going to melt it, and then I'm going to go up to 55. So every line segment where I have some dots, okay, and I don't know if you can see that super well because I draw it like microscopic because I kind of just draw it for me. But every little line segment is going to represent a calculation. So I have a line segment slanty one, a flat one, and another slanty. So I have 3 different calculations that I have to do in order to find the total amount of heat. So I know that my first one, my slanty one, that's going to be a Q equals MCAT, but it's going to be for ice, right? So my first Q value, okay, is going to be an MC delta T. And then I'm going to add to that the line segment, which is going to be an M delta H. And since it's melting, it's going to be of fusion. And then my third line segment is a slanty one, so it's going to be an MCAT, so an MC delta T again. Okay, now since I'm going that way, okay, that way. Since I'm going that way with my melting, my heat of fusion is going to be positive. Okay, so then you just plug it out. Now I would not put units in here so much. I would probably just put numbers. And not worry about the units so much as long as you're using the correct, what do you call these, constants, it should be fine. So I would say Q equals, okay, so it's 4.50 grams, right? And we're going from -3 to 55, but not all in one step. We have to do it in 3 steps. So 4.50 grams times, now for that first slanty line, it's under 0, so that is ice. So we need the specific heat for solid water, which is that one, so the 2.03. So we have 2.03 times the final of just that line segment. The final is 0, and the initial is -3. So 0 minus -3. Okay, plus 4.50 times the heat of fusion for water, which is positive 333, plus mass again, 4.50 times, now we're at the second slanty line, so we're above 0. So now it's a liquid. So now we use the specific heat of liquid water, which is 4.184. Okay, and the final temperature that we want to get to is 55, and it's still liquid at 55. So we're going to do 55 minus 0, not -3. We can only go to 0 because that's where that other slanty line started, is at 0. So it's going to be 55 minus 0. Most people don't really write the minus 0 because who cares? Most people don't write this 0 minus negative. They just put +3 in the box. And I'm just putting it there so you see where I got the numbers from, okay? All right, so then we stick it all in our handy dandy calculator, okay? So I'm going to do 4.50 times 2.03 times, and you could do it in parentheses if you want, 0 minus -3. Just make sure you put the negative sign and not the minus sign a second time because you'll get an error. All right, plus 4.50, oops, that's not an O. Oh, there we go, times 333 plus 4.50 times 4.184 times, and you can do in parentheses if you want, 55 minus 0. Okay, and we get that number. So now we look at our sig figs. Okay, now I kind of hate when things are like just one sig fig, but that's technically just one sig fig, and that's horrendous to me. I just hate that. So can we just, I don't know, can we change that to like 3.0, make it like 2 sig figs like the other temperature, because this temperature is 55 and I don't like that. So I'm just gonna make it 2 sig figs because that's horrendous. I don't know who wrote it. It wasn't me, but I don't like it. So let's make this 2 sig figs. So 2,561 down to 2 sig figs is 2,600. So your total Q value is 2,600 joules. Okay, and that's how much heat would be required to raise the temperature of 4.50 grams of water from -3.0 degrees Celsius to 55 degrees Celsius. Okay, so you can stick it all in your calculator one time. Yay, fun. All right. Now I realize there's some little algebra tricks in there that you could do instead of putting absolutely everything in the calculator, and that's fine. You do whatever you want to do as long as you show the work on the paper. We're good with that, okay? All right, so next one. It says, how much heat would be released upon cooling a sample of steam at 114 degrees Celsius to water at 11.5? All right, so again, I'm going to draw my little heating cooling curve in the left-hand margin, okay? And so, me. Okay, so I'm cooling, and notice it says released. So I'm cooling. It doesn't say what the mass of the sample is, does it? Cooling a mass. Oh, let's say it's the same sample up here. Let's say it's 4.50 grams. I don't know why it doesn't say. Let's say that's the mass, okay? So we're cooling this from 114 degrees. So let's say that's up here. That's 114, okay? And notice here, this is 100, okay? And we're going to go down to 11.5, and so that's going to be like here, right? So I'm starting at 114. I'm going to go down, and then I have a flat line. I'm going to go to the left, and then I have another slanty line where I'm going down, okay? So I'm going, okay? So that's my first Q value. It's a slanty line, so it's an MCAT, right? So it's MC delta T. Okay. And then my next slanty line, or my next line is not a slanty line, super sorry. It's a flat line. And so that's M times the heat of, and this time I'm condensing. I'm going from a gas to a liquid. So it's negative of the heat of vaporization. So it's negative of the heat of vaporization. All right, and then I have another slanty line. So that's an MCAT again. All right, so now I just plug in my numbers. So Q equals, so 4.50 times, and C over here, this is a gas, so I have to use the specific heat of gas. That's 2.01 times final minus initial. So for this slanty line, my final is 100 and my initial is 114. So it's 100 minus 114. All right, plus the mass again, 4.50 times the negative of the heat of vaporization, which is negative 2260 joules per gram. All right, plus another MCAT, so 4.50. And this time, this slanty line, it's a liquid between 100 and 11.5. So I'm going to use 4.184, the specific heat of liquid water, okay, times final minus initial temperature. Final is 11.5. Okay, minus initial is 100. All right, so now we again stick all of this in our calculator. Okay, I'll scooch this up so you can see. All right, so 4.50 times 2.01 times, in parentheses, 100 minus 114, all right, plus 4.50 times negative 2260, okay, plus the last one, 4.50 times 4.184, in parentheses, times 11.5 minus 100. All right, and we should get a negative number, okay? So now we look at our sig figs, okay? We've got 3 sig figs there, 3 sig figs there, 3 sig figs there, so let's make this 3 sig figs. So my Q value here is negative 10,300 joules. Okay, and that's the answer. And since the heat is released, it is a negative sign. Okay, all right. And now the last question is quite challenging. It's kind of fun though too. So it says, would a sample of 30.0 grams of ice at a temperature of negative 3.5 degrees Celsius melt if 2,055 joules of heat energy are added to it? and you need to provide mathematical proof for your answer. Okay, so we just need it to melt, right? So if we're looking at our heating curve, so I have negative, and then I don't really need the rest of this, but I'm going from negative 3.5, okay, and then there's 0, and I'm going from negative 3.5 to 0 and then to melt it, okay? So let's see. So I would probably say, okay, well, I've got 2 Q values I need to overcome here. So my total Q value is going to be, first I have a slanty line, so that's an MC delta T. And then I've got a flat line, so that's an M delta H. And I'm going to the right, so it's positive, and it's melting, so it's the heat of fusion. Okay, so I can plug that in. It's 30.00 grams. I've got the mass, I've got my initial temperature, and I know my final has to be 0 if I just want it to melt. That means it only goes to 0. And this is how many joules I have. So let's see how many joules this requires and see what will happen. So, all right, so I can do 30.00 times the specific heat of ice, which is 2.03. Okay, times final minus initial. So final is 0 and initial is negative 3.5. So 0 minus negative 3.5 is positive 3.5. All right, plus mass again, so that's 30.00 times the heat of fusion, which is 333. All right, and let's see what we get. Okay, so 30, oh, you can't see that, sorry. 30.00 times 2.03 times 3.5 plus 30 times 333. Okay, and so that's going to require 10,203.15 joules. So if I only have 255 joules, will it melt? No. But we can see if some of it will melt. So let's just see just what this portion is right here. Okay, let's just see just what this part is, just to raise it to 0. So that's 30.00 times 2.03 times 3.5. Just that portion, okay? And that's 4 sig figs, and that's 2, so we'll go with 2 sig figs. Just this portion is 210 joules. Okay, so I have enough energy. I have 2,055 joules. I have enough energy to at least raise the temperature of my water. So if I do 2,055 joules minus what it takes to heat up the water, okay? Okay, I get 1845 left over. Now, the Q to melt is Q equals M times heat of fusion. So I can actually figure out what my mass is because I know the heat of fusion. So if I just divide both sides by 333, let's see, 1845 divided by 333, I get 5 point, let's see, my original, well, that's 4 sig figs technically, so 5.541 grams. So what this means is that I can melt some of the water, but I can't melt all 30 grams. So would a sample of 30.00 grams of ice melt from negative 3.5? No. But only 5.541 grams will be able to melt. So yes, some will melt, and you can actually figure out the exact amount to melt. And that's the end of the lesson and the end of your thermochemistry notes.